we're going to talk about the Eckmann Hilton argument. The Eckmann Hilton argument was originally used to show that all higher homotopy groups are abelian, that is, for the pi 2s and above are all abelian. But we can use it to show all sorts of other exciting things as well, such as the fact that a bicategory with only one 0 cell and one 1 cell is a commutative monoid. And also that a monoid object in the monoidal category of monoids is a commutative monoid. That's a bit of a tongue twister, that one. But first of all, let's just see what the Eckmann Hilton argument is. What it says is that if you're given a set with two binary operations on it, both of which are unital, then in fact those two binary operations must be the same and commutative. So it sort of says you can only fit one binary operation into a set. There isn't enough space for another one, as long as those two binary operations interact in some certain coherent way, which we'll now see. So here's the Eckmann Hilton argument. Eckmann Hilton argument. So given a set with two binary operations, which we'll write as circle and star, satisfying the following properties, such that 1, circle and star are unital with the same unit, and secondly that one of them distributes over the other, which is to say that A star B circle C star D equals A circle C star B circle D. So what's happened here is that we've switched the order of the star and the circle, and in doing so we've switched around these middle two things that we're multiplying together. So given this situation, then what do we have? Then circle equals star, as it were. Those two operations are the same, and the operation is commutative. So, before I say anything else, let's just think about this condition here for a second. You might think that this condition looks very mysterious, but let me give some geometric idea behind it in the hope of making it more obvious. Now, I've written these as star and circle to be suggestive, as usual, because these could be vertical and horizontal composition of two cells in a bicategory. So if we write a circle B like this, A, B, and if we write a star B like this, the horizontal composition, then what does this become? Well, this is A star B. That wasn't very straight, was it? A star B circled with C star D, whereas this one is A circle C starred with B circle D. Oh look, this is something we recognize as the interchange law. So what we're saying is that if we satisfy the interchange law and the fact that these two are both unital with the same unit, then we can show that these operations are the same and commutative. We'll later see that we can actually drop condition 1, but it's useful to use it now. So what I want to do is show how we can prove that this is true, very geometrically, going round the Eckmann Hilton clock, as follows. So what we've got here, we're trying to show that A star B equals A circle B, and that they're commutative. So let's put up here A star B. And down here, at 6 o'clock, I'm going to put B star A. Okay, now at 3 o'clock, I'm going to do the vertical ones. So here we're going to have A circle B, and here at 9 o'clock we're going to have B circle A. And what we're going to do is we're gradually going to move the B around the A, and we're going to see how they move around each other in this clock. So there's 12 o'clock. At 1 o'clock, what we're going to do is we're going to insert some units. So B is the same as 1 circle B, and A is the same as A circle 1. So we're going to do that. Now we can hit it with the interchange law, so that we have B and 1 side by side, and we have A and 1 side by side. And then we can collapse these sideways, so B composed with 1 sideways is just B, and 1 composed with A sideways is just A, so we do indeed get that. And now we can carry on, right? So we're now going to keep moving them in this direction. So here we're going to do B with 1 on that side, and we're going to do A with 1 on this side. Now we're going to perform the interchange law to get 1A here and B1 here, and now we can collapse B vertically and collapse A vertically here, and we get this sideways. Woo! We've got ourselves commutative. Now we can just finish off to make the entire clock. So it should be obvious. You should in fact be able to fill it all in yourself now. So we have B. No, that was completely wrong. That was wrong in almost every possible way. Let's try it again. Like this. Now we use interchange, A1, 1B, and now we go around the other way for the last bit. So at 10 o'clock, whoops, we have A1 here and B1 here, and then we perform interchange, and we get 1B, A1, and that brings us back to there. So we could, if we really wanted to, write out the algebra of this as well, because this is A star B, and this is A composed with 1 star 1 composed with B, and this one is A star 1 composed with 1 star B, and that's the same as A composed with B. So I'm not going to go all the way around. You can certainly fill in the rest of the algebra for that yourself. The last thing it's interesting to note is that here we did use the fact that the vertical unit and the horizontal unit were the same thing, because look, we used this as a vertical unit, then we did the interchange and we showed that it was a horizontal unit. But if you used different units and you use them in a judicious enough way, you could show that actually you can deduce first the fact that the two units are the same, and then you can go around this clock. So I wonder if I can produce that off the top of my head. Supposing that the vertical unit is called V and the horizontal unit is called H. So what we're probably going to do, I'm sure this is going to go horribly wrong here, is, you know what? I'm not going to dare to try and do it off the top of my head like this. I'm going to leave it as an exercise for you at home and leave it there. Well, last time we talked about the Eckmann Hilton law, but I chickened out of showing the two slightly curious facts about it, which is that you can deduce that the two operations have the same unit. You don't have to assume it. And the other thing you can deduce is that they are both associative, and you don't have to assume that either. So the way to do it, remember that the Eckmann Hilton law says that if you have two operations, circle and star, which we're going to write as horizontal and vertical composition, so this one's vertical composition and this one's horizontal composition, then if you've got the fact that, if you've got interchange, which basically says this, then you can deduce that both the operations are the same and commutative. But you have to, what we used when we went around that clock was the fact that they both have the same unit. And in fact, we can deduce that. So if we say that V is the vertical unit, so V vertically composed with A in either direction is A, and if we say that H is the horizontal unit, so H, horizontally composed with A on either side, is A, then what we can do is we can cunningly use both V and H at the same time. So if we put a V and an H here, and a V and an H here, then what we get this way round is that that's the same as doing, well, V vertically composed with H is just H. And here it's also just H, so we get H, and that's just H, because H vertically composed with H is H, horizontally composed with H is H. But if we now use the interchange law here, then we do this the other way around. So now we get that V horizontally composed with H, well now it's H that's acting as the unit here, so we just get left with V at the top, and we also get left with V at the bottom, and now we're vertically composing the vertical units, so what we get is V. So look, we've got that H equals V, showing that the two different units are the same. Now we can do a similar sort of trick for associativity. So for associativity, but this time the thing that we're going to use has to involve an A, a B, and a C. So we're going to put our A here, our B here, and our C here, and a random unit there. Well, if we do this way round, what we get is we get A composed with 1, let's put it over here. We get A vertically composed with 1 starred with B vertically composed with C, right? But star and circle are the same, and that's the unit. So that's the same as just A circle B circle C, right? But now if we do interchange on it, we get C1 and BA here, and what's that? That's A horizontally composed with B circled with 1 horizontally composed with C, but what's that? That's just the same as A circled B, because circle's the same as star. This whole thing is the same as C, so we get C. So we've got that this way of parenthesizing A, B, C is the same as that way, so we've deduced associativity. So that's quite fun. Now, the reason I've been using horizontal and vertical composition as the example is that this is what you can do if you're in a 2 category. So here's an example of applying the Eckmann Hilton argument. 2 category with only 1 0 cell and only 1 1 cell. 1 0 cell and only 1 2 cell is in fact a commutative monoid. So what's a commutative monoid? It's a set equipped with a commutative operation. Well, the underlying set that we're going to use is the set of 2 cells. So I suppose this needs to be small. So the set, the underlying set, is the set of 2 cells. And the operation, well, we can either take it to be circle or star. Well, we've got 2 operations. We've got circle and star, but they satisfy the Eckmann Hilton argument. So what we get is that they're the same and they're commutative. So they're the same. Now you might ask me why I used a 2 category here and not a bi category. I did the strict case because that's easier. The bi category case is a bit more complicated because in fact horizontal composition in a bi category is not strictly unital. So you have to faff around a bit. It does come out all right in the end, but you do have to faff around a little bit in order to make it work. And so what you have is the following slightly interesting situation where if you start with a bi category, if you only have 1 0 cell, what you get is a monoidal category. one cell as well, then what you have is a commutative monoid. You actually get something a little bit more complicated than a commutative monoid because you also have a distinguished invertible element left over from the unit constraint in the bicategory. But I'm not going to go into that now.